Hi everyone, welcome to Basis and Dimension Part 4. In this video, we will learn quotient space and dimension of quotient space. Okay, now come see what is a quotient space. Let W be a subspace of a vector space V of F and alpha belongs to V. Where is alpha? Alpha belongs to V. The set W plus alpha is equal to gamma plus alpha, where gamma belongs to W is called a right coset of W in V. Already you know cosets in group theory. So here also W being a subspace, it is a vector space, and not only it is a vector space, you can treat that as W plus is a group, is an abelian group. So because it is a group, you can define its coset. Take an element alpha belongs to V, then W plus alpha is equal to gamma plus alpha, where gamma belongs to W is called a right coset of W in V. Similarly, the set alpha plus W is equal to alpha plus gamma, where gamma belongs to W is called a left coset of W in V. Now you are having the right coset and left coset. Suppose if you consider the set of all cosets of W in V, and it will be denoted by quotient set, that is QUO, quotient set. What is the quotient set? It is nothing but the set of all cosets alpha plus W such that alpha belongs to V. Alpha belongs to V is called quotient set. Alpha belongs to V. Okay. Now this is the quotient set. When will you say that this quotient set is a quotient space? If it becomes a vector space, it will be the quotient space. Now, in order to say that it is a quotient set, you have to consider the quotient set, and it is denoted by V by W. Quotient set is denoted by V by W. Now, you want to say this quotient set is a vector space, then that set will be quotient space. Okay. In order to say that this is a quotient space, you have to define vector addition and scalar multiplication. That vector addition and scalar multiplication is defined as addition of cosets and scalar multiplication of coset. See how we are going to define and how we are going to show that any quotient set is a quotient space. Okay. Now see here the theorem. Like let W be a subspace of a vector space V of F, then the set V by W is a vector space over F for the vector addition and scalar multiplication defined by. Now see the vector addition. Now what is V by W? V by W is a set which consists of all cosets. W plus alpha is a coset where alpha belongs to V. This is the coset. Now this is the quotient set. On this quotient set, you have to define vector addition and scalar multiplication. See how the addition is defined. W plus alpha is one element in V by W, and W plus beta is another element in V by W. The addition of these two is defined as W plus alpha plus beta. Where are alpha and beta? They are in V. Okay, what is V? V is a vector space for which W is a subspace. Now is it clear? Now the coset addition is defined like this. Now see the scalar multiplication, how the scalar multiplication is defined. W plus alpha is an element in V by W. A is an element in F. A into W plus alpha is equal to W plus A alpha. for every A belongs to F and alpha belongs to V. Now is it clear? Now with respect to these two operators, this set of cosets will form a vector space. That means using these two operations, whether this set of cosets is satisfying all the properties of vector space or not, we have to verify. Now we are going to do that. Before going to proceed to verify the conditions of vector space, what we are doing in this theorem is, this is coset addition and coset multiplication we defined. Is it? The definition is well defined, we have to conform ourselves. Coming to mathematics, there are definitions which are universally accepted and there are some definitions locally accepted. Locally accepted means we will define some definitions to prove that theorem or that will be useful in that branch. It may not be useful in other ways. That is the locally defined. That means if we are defining the definition of cosets, it is locally defined. We have to say, conform ourselves it is well defined. That we are going to see. Now what we are going to do? Now we want to show that this set of vectors, the vectors are here, the cosets. This set of vectors will form a vector space with respect to these two defined operators. Now these two operators are well defined. That thing we have to conform ourselves. See how we are going to do it. Given that V of F be a vector space and W is a subspace and W be a subspace of V. Okay, that you have taken. Now what we are going to do, the two compositions or the two operations what we are defined as vector addition and scalar multiplication, we are going to say that they are well defined. Now see, suppose W plus alpha is equal to W plus alpha dash. From the properties of cosets, you can say that alpha minus alpha dash belongs to W. Okay. Similarly, if you take W plus beta is equal to W plus beta dash, beta minus beta dash belongs to W. It is also from properties of cosets. Now what is this? Alpha minus alpha dash belongs to W, beta minus beta dash belongs to W. But what is W? W is a subspace. Therefore, closure property satisfies. So you can say that alpha minus alpha dash plus beta minus beta dash belongs to W. Is it or not? So from this you can say that alpha plus beta minus alpha dash plus beta dash belongs to W. Can I say? We can arrange it. Now see, alpha plus beta minus alpha dash plus beta dash belongs to. That implies W plus alpha plus beta is equal to W plus alpha dash plus beta dash. Is it? Now this, according to the definition, it is W plus alpha plus W plus beta, and this is W plus alpha dash plus W plus beta dash. Therefore you can say that the addition in V by W is well defined. Okay. Similarly, we will see the scalar multiplication. Suppose alpha minus alpha dash belongs to W. Alpha is in W, alpha dash is W, therefore alpha minus alpha dash belongs to W. Now take A belongs to F. A into alpha minus alpha dash belongs to W. By vector scalar multiplication, it is A alpha minus A alpha dash belongs to W. Apply the coset properties. This implies W plus A alpha is equal to W plus A alpha dash. Therefore, scalar multiplication in V by W is well defined. That means you want to show that V by W is a vector space. In order to show that V by W is a vector space, it should be equipped with two operators called vector addition and scalar multiplication. That means you have to define the addition of vectors, that is V by W is the set of all cosets. how you are going to add the cosets you have to define, how the scalar multiplication will be in the set of cosets you have to define. That we have done. And after defining that, what we are defined is well defined, we are confirming once again. Okay, now with respect to those two operators, the set of cosets, that is V by W, with respect to this plus and dot. Now this plus will represent the addition of cosets, this dot will represent the scalar multiplication of cosets. Will form a vector space that we are going to see. Now in order to see that, first we will see whether closure property satisfies or not. Now what you have to say, if you want to say V by W is a vector space, first you want to prove V by W is abelian. V by W is abelian. In order to show that V by W is abelian, what closure property should satisfy, associativity should satisfy, there exists additive identity, there should also exist additive inverse, and commutativity should also satisfy. If all these 5 properties are satisfied with respect to the defined vector addition, then we will say that V by W is abelian. Now see here, let W plus beta belongs to V by W for every alpha beta belongs to V. Okay. Now how the addition is defined? W plus alpha plus W plus beta is equal to W plus alpha plus beta belongs to V by W. According to the definition of the cosets of V by W, alpha plus beta belongs to V means it will belongs to V by W. Therefore, closure property satisfies. How you are saying this belongs to V by W? Since alpha belongs to V, beta belongs to V, V is a vector space, alpha plus beta belongs to V. Okay, that means in V by W with respect to addition, you are able to show that closure satisfies. First property, what you are able to show? Closure satisfied. Closure satisfied, is it? Now see the next one, associativity. In order to verify associativity, consider 3 elements, W plus alpha, W plus beta, W plus gamma in V by W. For every alpha, beta, gamma belongs to V. Okay. Now consider W plus alpha plus W plus beta plus W plus gamma. According to the definition, this will be W plus beta plus gamma. W plus alpha plus that. Again apply the definition. This will be W plus alpha plus beta plus gamma. Now where are alpha, beta, gamma? They are in V. V is a vector space. Therefore associativity satisfies in V. So alpha plus beta plus gamma can be written as alpha plus beta plus gamma. So this again you will write W plus alpha plus beta. These two together you will write W plus alpha plus beta plus W plus gamma. Therefore, associativity satisfies in V by W. Now is it clear? So, first one closure satisfies, second one associativity satisfies. Now see next identity. Now take W plus 0 bar, W plus alpha, where 0 bar and alpha are in V. Okay. Now W plus alpha plus W plus 0 bar is equal to W plus alpha plus 0 bar. This will be equal to W plus alpha. So you have taken W plus alpha and you are added W plus 0 and you got it. Again W plus 0 plus W plus alpha is equal to W plus alpha. So any element is added to some element and you are getting the same element, means that element will be the additive identity. So here what is the additive identity? W plus 0. Is it? W plus 0 can also be written as W. So W is the additive identity in V by W. Okay. W is the additive identity in V by W. So identity exists. Okay. Now see the next one. Inverse. Let W plus alpha, W plus minus alpha belongs to V by W. You can take like that because alpha belongs to V. V is abelian. V plus is abelian. For every alpha there exists minus alpha belongs to V. Since minus alpha is in V, W plus minus alpha will be in V by W. So W plus alpha plus W plus minus alpha is equal to W plus alpha plus minus alpha, that is W plus 0. Therefore, W plus minus alpha plus W plus alpha is also equal to this. That means there exists additive inverse. For W plus alpha, the additive inverse is W plus minus alpha. So, what you are able to say? Closure satisfies, associativity satisfies, there exists additive identity, there exists additive inverse in V by W. Still commutativity. Now see, W plus alpha, W plus beta belongs to V by W. For every alpha beta belongs to V by W, W plus alpha plus W plus beta is equal to W plus alpha plus beta. Now, that will be alpha and beta are the elements of V. V plus is abelian group, so commutativity satisfies. Alpha plus beta can be written as beta plus alpha. So, this will be W plus beta plus W plus alpha. So, according to the defined coset addition, V by W is abelian. Is it? V by W is abelian. That is, first set of properties to be the vector space is satisfied by V by W. Now, second will be what? That is closed. It is already proved. Now, see here. Next one. A belongs to F. W plus alpha, W plus beta belongs to V by W. For alpha, beta belongs to V. That means you are going to verify whether the distributive laws are satisfying or not. That is the third set of properties you are going to verify. So, you are taking W plus alpha and W plus beta in V by W and A in F. This is A into W plus alpha plus W plus beta. According to the addition of cosets, it will be W plus alpha plus beta into A. So, this is by definition of coset multiplication, this will be W plus A into alpha plus beta. That is W plus A alpha plus W plus A beta. Again apply the coset multiplication definition. This will be equal to A into W plus alpha and this will be equal to A into W plus beta. Therefore, the first one is satisfied. In the third set, first property is satisfied. See again, A comma B belongs to F, W plus alpha belongs to V by W and for every alpha. Now take A plus B into W plus alpha. This will be according to the definition of coset multiplication, A plus B into alpha. Again separate and W plus A alpha plus W plus B alpha. That is, you are separating by using the coset addition. Now this will be W plus A alpha plus W plus B alpha. That is A into W plus alpha plus A into W plus alpha. So, okay, now plus B into W plus alpha. This will be equal to A into W plus alpha plus B into W plus alpha. Is it? Now, therefore, two distributive laws are satisfied. Is it? The first one and the second one. Now, here third one, associativity. Let AB belongs to F, W plus alpha belongs to V. This is AB into W plus alpha. Consider, apply the coset multiplication definition. This is W plus AB into alpha. That will be W into A into B alpha, because AB alpha, AB are belonging to F, alpha belongs to V. V is a vector space, therefore that you can write it. So, this is A into W plus B alpha, that is A into B into W plus alpha. Okay. Now, see the one more property, 1 into. Now, 1 into W, 1 belongs to F. 1 into W plus alpha is equal to W plus 1 alpha, that is W plus alpha. This shows that all the postulates of vector space are satisfied. 9 postulates you have verified. One from the scalar multiplication, that is well defined, you said from the definition itself. So, all the 10 postulates are satisfied by V by W. So, what can you say? V by W plus and dot is a vector space. What is this plus? Vector addition. Here what are the vectors? The vectors are cosets. W plus alpha, W plus beta. These are the elements of V by W. Is it? V by W is the set of all cosets. So here in this vector space, the vector is a coset. Is it? Now see the beauty. In vector spaces, you can see ordered triple as a vector, ordered n triple as a vector, ordered pair as a vector, or a matrix is a vector, or a continuous function is a vector. Like that, you here the coset is a vector. The coset is a vector. Now see, what is a coefficient space? Any coefficient set, the set of coefficients, that is V by W, is satisfied with respect to addition of cosets and multiplication of cosets, the postulates of vector space, then that set of cosets is said to be the quotient space. See how the definition. Let W be a subspace of a vector space V of F, alpha belongs to W, then W plus alpha is equal to gamma plus alpha, where here alpha belongs to V, not W. Alpha plus gamma belongs to W is called a right coset in V. Similarly, this is the alpha plus W is a left coset of W in V. The set of all cosets of W in V is denoted by V by W, and this set will become a vector space with respect to the vector addition of cosets and scalar multiplication of cosets, and that is called as quotient space. Now you will be asked in 1 mark questions, define quotient space. What do you mean by quotient space? Otherwise, then you have to write the quotient space like this. Okay. Now, see the next theorem. What is the next theorem? Means this is, now you define the quotient space. Now, dimension of quotient space. Now, dimension of quotient space is, when will you say that, what do you mean by dimension? The number of elements in the basis set is said to be the dimension of a vector space. Now what you said, V by W is being the set of all cosets, it is becoming a vector space with respect to the vector addition of cosets and scalar multiplication of cosets. Is it okay? Now if dimension of V by W will be equal to dimension of V minus dimension of W. Now W be the subspace of finite dimensional vector space V of F. What is W? W is subspace of finite dimensional vector space. You have done one theorem. Any subspace which is a subspace of finite dimensional vector space will also be of finite dimensional. So since V is a finite dimensional, W being the subspace of finite dimensional vector space, the dimension of W will also be finite. Now you are going to prove that dimension of V by W is equal to dimension V minus dimension W. For that, see what you are going to take. You have taken W as a subspace of finite dimensional vector space V of F. It is given to you. So dimension of W is finite. So let us assume it is equal to M. You have taken dimension of W is equal to M. Let B is equal to alpha 1, alpha 2, alpha M be the basis of W. Why? Because dimension of W is M. Dimension is defined as the number of element in the basis set. So with M elements as the basis set of W you have considered. B is having M elements and you are saying that it is the basis of W. Okay. Since B is the basis of W, by definition of basis set, what will be B? B is linearly independent and L of B is equal to W. Is it clear? Okay. What is W? W is the subset of V. And where is B? B is linearly independent subset of W. Being the linearly independent subset of W, B will be the subset of V. Okay. B is a linearly independent subset of V. According to the extension theorem, either B itself will be a basis or B can be extended to form a basis. Here you have taken B can be extended to form a basis of V. Okay, now see, B, that means you are adding some elements beta 1, beta 2, beta t to B, and you are saying it is the extended set of B and it will form a basis for V because according to the extension theorem. So the number of elements in the basis set of V is m plus t. So dimension of V is equal to m plus t. Now what is your theorem you have to prove? Dimension of V by W is equal to, you have to prove that dimension of V minus dimension of W. Is it or not? Now what is dimension of V? You got it as m plus t. Is it? And what is dimension of W? It is m. So what is remaining? T. That means dimension of V by W is equal to T. This we have to prove. What we have to prove? Dimension of V by W is equal to T we have to prove. In order to prove that, we will take a set with the number of elements as a T, and if we show that it is linearly independent and it is that L of that set is equal to V by W, our problem is over. For that, consider S dash is equal to W plus beta 1 plus W plus beta 2 plus so on W plus beta t. That is, these are the elements in the set of cosets, quotient space, is it? So S dash with T elements you have taken. Now what you are going to prove? S dash is linearly independent subset of V by W and L of S dash is equal to V by W. That you are going to prove. Is it? Now see. Now how to show that S dash is linearly independent? In order to show that S dash is linearly independent, you have to consider the linear combination of that set of elements and equate it to 0 bar. Now what is linear combination of the set of elements S dash? B1 into W plus beta 1, B2 plus B2 into W plus beta 2 so on, plus BT into W plus beta t is equal to W plus 0 bar. Why you have taken W plus 0 bar in place of 0 bar? Because W is the additive identity of the quotient space V by W. Okay, therefore you have taken it as a W plus 0 bar. Now according to the definition of coset addition, you will write it as the first is coset multiplication, scalar multiplication of cosets, W plus B1 beta 1, W plus B2 beta 2 and so on, W plus BT beta t. So, and this will be by adding, you will get W plus B1 beta 1 plus B2 beta 2 plus so on is equal to W plus 0. This implies by properties of coset, B1 beta 1 B2 beta 2 and so on belongs to W. But what is W? W is equal to L of B. Now because W is the B is the basis, so this element belongs to L of B. But what is B? L of B, any element in B, W can be expressed as a linear combination of basis elements. So this can be expressed as A1 alpha 1 plus A2 alpha 2 plus so on, AM alpha M. Therefore, A1 alpha 1 plus A2 alpha 2 plus so on, AM alpha M, and bring all these terms to the side and equate it to 0. Now what are they? Alpha 1, alpha 2, alpha M, beta 1, beta 2, beta t. They are the basis elements of V. Therefore, their linear combination is equal to 0 implies, according to linearly independent set, all the coefficients existing in that set will be equal to 0. Why? This is alpha 1, alpha 2, alpha M, beta 1, beta 2, beta t belongs to basis set of V. Being basis set, that set will be linearly independent. Since it is linearly independent, their linear combination equal to 0 implies all the constants existing in that combination is 0. Therefore, B1 is equal to B2 is equal to B2 is equal to 0. Therefore, S dash is linearly independent subset of V by W. Now, we want to show that L of S dash is equal to V by W. Now, in order to show that L of S dash is equal to V by W, you have to prove L of S dash is a subset of V by W, and V by W is subset of L of S dash. Okay. Now, in order to show this is clear, L of S dash is V by W, already it is clear, it is obvious. Now, we will show that V by W is subset of L of S dash. In order to show that, consider W plus alpha in V by W for every alpha belongs to V. Is it? Now, you have taken W plus alpha in V by W. Now, alpha belongs to V. V is equal to L of S implies alpha belongs to L of S. Therefore, alpha can be written as a linear combination of the elements of S. Is it? What are S elements? Alpha 1, alpha 2, alpha m, beta 1, beta 2, beta t. So, alpha is the linear combination of the elements of S. Okay. Now, you will write it as alpha is equal to this part, you are denoting it as gamma. Gamma plus d1 beta 1 plus d2 beta 2 plus so on dt beta t. Okay. Now, this will belongs to, this gamma will belongs to L of B being the basis element, basis linear combination of basis elements, and that is equal to W. Okay. Now, see here, this is W plus alpha will be equal to W plus gamma plus this, is it? But W plus gamma, I will say it is equal to W because gamma belongs to W. Okay. Now, that is the property of coset. H is equal to H is equal to H. There the coset is with respect to multiplication. Here the coset is with respect to addition. Therefore, W plus d1 beta 1 plus d2 beta 2 plus so on dt beta 2. So, if you separate it by the definition of vector addition of cosets, W plus d1 beta 1 plus W plus d2 beta 2 plus so on, it is plus W plus dt beta 2. Again, separate by coset multiplication, that is scalar multiplication of coset, d1 into W plus beta 1 plus d2 into W plus beta 2 so on. This belongs to L of S dash. Therefore, V by W is subset of L of S dash. Already you said that L of S dash is V by W, subset of. Therefore, L of S dash is equal to V by W. Therefore, S dash is a basis of V by W. Therefore, dimension of V by W is equal to T. Hence, the statement follows. Dimension of V by W is equal to dimension of V minus dimension of W. Okay. Thank you.